serve as a good mechanical engineering principle and practices review or introduction if you're not a ME, and then we kind of take it to the intermediate, and in some cases a little bit advanced level, and so you'll see that it'll be a very broad program, just like the discipline itself, mechanical engineering, which is broad, which covers not only machine design as the term mechanical applies, but fluids, piping and air conditioning, thermodynamics, dynamics, kinematics, kinetics. It even covers a beam analysis, even though that kind of gets into the that's where the lines blur between mechanical and civil. But there, when you, as a mechanical, if you're designing beams and the structures and the mechanical end of things and the material aspects of things, you need to understand how the civils are going to end up using them, and so you can better design or take all the factors into consideration. So we'll get into a little bit of beam analysis, we'll get into a little bit of truss analysis. So it's a very broad a set of topics that we cover in here. You see the whole list of them. We'll start with system of units, and then we'll cover some tools that are commonly used by mechanical engineers and technicians, and then we'll get into materials and mechanics of materials. So there's that material science component to mechanical engineering that will incorporate in here in the program, and that's when we get into statics and do a little bit of beam analysis. We get into bending moment diagrams, shear force diagrams. We get into truss analysis and all that good stuff, and then we get into dynamics, which includes kinematics, where forces are ignored, meaning not taken into account in the analysis. That's that part of dynamics. But dynamics where forces are considered, and when we say forces, we mean unbalanced forces that typically will result in acceleration, and that study of dynamics is called kinetics. We'll cover that. Then we get into thermodynamics, and that portion, very short coverage of thermodynamics is borrowed from our 8-hour thermodynamics program that we do over one day, and we just did that this past week. And so in that program, we again get much deeper into thermodynamics. That's our main focus, and then get into HVAC a little bit as well. So and that's based on a book I published some years ago titled "Thermodynamics Made Simple" for energy engineers, but it's really designed for all engineers. We'll get into the refrigeration cycle, which basically is tied into HVAC and technically is part of thermodynamics. But anyway, we'll get into a little bit of that today, and then we'll get into fluid mechanics, fluid statics, fluid dynamics, which is a short excerpt out of a whole day program that we do titled Hydrostatics and Hydrodynamics. So if you need to dig deeper into that, but we do some fluid, get deeper into fluid flow calculations and static fluid calculations, a lot deeper than we will here today. So, and then we'll cap off the program tomorrow, by the end of the day tomorrow, with a little bit of engineering economics review or introduction, you may call it, where we basically kind of highlight the importance of time value of money when you do your mechanical, or for that matter, any engineering project financial justification. So that's the roadmap for the 2 days, and don't see any questions out there, so we'll continue to dig into the program. All right, so and by the way, just a quick okay, so let's talk about system of units. And so what we do, instead of throwing a bunch of equations at you, what we do is we do a bunch of take care of a bunch of things by covering discussion of units, and at the same time define those concepts and maybe put a few equations out there. So so that's what we're going to do. And so to start off with, you see the title is Basic System of Units, but under that you see when we talk about one of the most basic entities in mechanical engineering, it is indeed length or distance. And length or distance can be either linear or angular. So so the difference is, of course, linear is when you are measuring distances or lengths in a linear fashion, as if you're walking, you're measuring something along the floor, that's linear. Measuring something on the table, that's linear. You're going from point A to point B in a linear direction. While angular would be when you, instead of linear movement, you have angular rotation. And when you have angular rotation, that also involves displacement or distance traveled, or basically the amount of angular distance covered. So when you're dealing with angular motion, you are basically focusing on angular distance covered, and we'll explain the units in a second. So linear units for linear distance measurement. Let me put something up here real quickly. And so as far as equations are concerned in mechanical engineering, in dynamics and statics and so forth, the distance can be sometimes represented by d. Okay, but more commonly it is s. Okay, and so distance really is distance covered, meaning what you would measure from point A to B. But s is typically a function that it's a function of time. So it is a positional function as a function of time. So in other words, s represents a position, and when you put in s as s with t in parentheses next to it, it represents a positional function, meaning it's telling you that the position in this in some system is changing as a function of time. So how do you identify the position quantitatively? You do that numerically and quantitatively through coordinates. So that's basically how you would represent s. So in three-dimensional coordinates, where you have x, y, and z representing those respective axes, three-dimensional axes, your origin would be at 0, 0, 0. And so that's, and then at another point in space, it could be 1, 0, 0 or 1, 1, 1 or something, as the location changes, position changes with time. So that's what s of the function of t is. So overall position and distance are measured in different units, depends on the unit system you're working within. And mechanical engineering is that arena where, unlike electrical, which is your discipline there, unlike electrical, most of the mechanical engineering in the United States is, or majority of it is done in U.S. units. But there's some that is still, done in metric units. Some people prefer to work in metric units, including myself, primarily because the equations are more basic that way, and less confusion with the GC factor, the gravitational constant factor, which I'll share with you in a little more detail in just a minute. And so anyway, the linear distance, a small distance or small amount of length or measurement can be measured in mils, which is 1/1000th of an inch. And then you have inches, and you have feet and yards and miles. That's all British unit system, which we have adopted, and we call it U.S. customary unit system. And it's also referred to as the imperial unit system. So while in electrical, as you know, that being your discipline, Paul, the majority of the unit system units that are utilized in electrical are basically metric. So with a few exceptions, and which is something that we cover in our electrical engineering practice principle and practices program. We have a one-day of it scheduled later on this week on Friday. If you have somebody who's interested in it, it's a kind of a abridged version of a two-day program that we do more commonly. But anyway, so in the metric unit system, distances and lengths are measured in micrometers, which would be a very small or essentially 1/1,000,000th of a meter. But the basic unit in metric arena or SI arena is meters. You measure lengths or distances in meters. And what do we mean by basic unit? Well, when you hear me say or use the term basic, over the next 2 days, you will basically what it implies is we're using units that the equations are designed to be utilized in. If you use non-basic units in standard physics equations, you're going to end up getting a wrong answer. Meaning, plugging in micrometers when the equation really is based on meters. Plugging in kilometers when the equation really works in meters. Well, same thing with even U.S. customer unit system. Plugging in inches when the equations, most physics equations in U.S. customer unit system are based on feet. So, or plugging in yards when the equation is really based on feet. So want to make sure that that when you're working in the U.S. unit system, the length or distance is measured in feet, and in metric unit system, it's expressed in meters. Even though we have other versions or forms of these units like millimeters, centimeter, micrometer, and kilometer, and so on. And then as far as the angular position or distance is concerned, a very basic unit for measurement of distance would be revolutions. So you see RPMs are utilized in equations of different types to calculate various things, like, for example, one of the equations that helps you convert torque or to power and power to torque. That's I think if I remember it right, it's if you're working in U.S. unit system, it is your torque would be equal to some multiple